I will switch off my video, stop my video.
It's totally fine. So while we are waiting for other people to show up, if you have any questions, I mean,
I will switch.
If you have any question, please write it in Q&A, or you can raise your hand and you can ask the question directly. We will start in about 2 minutes, waiting for others to show up. So, yes, today we will go through this. Yes, Moby. Of course. So when I was reviewing the previous lecture, I just realized that okay, so I realized that unfortunately I didn't go through the gauge problem that was asked by one of the students or one of the attendees here, and I will go in about 10 minutes going through the gauges and what the gauge means, and after that we will I think we will close the entire of the chapter 1 without having any problem. So the problem of gauge is coming back to the question of the scalar and vector potential. Well, we described that if you go with a vector potential, specific vector potential of A, if you, for example, we know that B, magnetic field, is an observable quantity, so we can go to the laboratory measuring it. And also on the other side, E, which was given by minus gradient of phi minus the time derivative of A. And remember that we are talking about not static electrodynamics. And we, of course, I mean, we drive these from Maxwell equation. They are satisfying Maxwell equation. So if you take the divergence of B, which is the divergence of a curl that is equal to 0, and if you take the divergence of E, then what you will get from this equation, sorry. If you take the curl of E, which is curl of minus gradient of phi minus time derivative of A, then you will have curl of minus gradient of phi, and then we have minus time derivative of a curl of A. The first term, of course, is 0. The second term, indeed, is equal to minus time derivative of curl of A, which is B. So, well, we know that those are the electric field and magnetic field, which magnetic induction, which they satisfy Maxwell equation. So, well, and previously we say that if here in this equation, if I take A and replace it by A plus gradient of any scalar, then still B is the same. B, which is curl of A, is still the same as the curl of A plus gradient of lambda. Okay, which these are the same. Nothing had changed. So, and that raises a question if A is has a physical meaning or not, because you can change it by by any gradient of lambda. And well, we only looked at the B term. So that was only the B term. But also we know that A has a contribution to the electric field. Let's do that calculation and see what is happening with electric field. Electric field, we say that, well, if you have a phi and A, then electric field is given by minus gradient of phi, as I described in the uppercase, and the time derivative of A. Now, what happens if A is changed to be A plus gradient of lambda? Should I change? And the question is that, first of all, if I change A to be A plus gradient of lambda, B does not change, but what is happening with the electric field? And if electric field does not change, that's excellent. But what is happening if electric field is changing? Should I change? Should we change phi as well? And if it's yes, what is the form? What will be the form? Okay, so, well, I will change it. I will say that now I calculate minus gradient of phi minus time derivative of new A, which is A plus gradient of lambda. Well, I will clearly say that the time derivative of gradient is not equal to 0, so it will be minus gradient of phi minus time derivative of A minus time derivative of gradient of lambda. Okay, so let's move them around in such a way that I will get something interesting. So I'll write it minus gradient of phi. That term, I will bring it here, and I will swap gradient and derivative. Then what I will get, the new term, which is I have it here, it will be, excuse me, plus gradient of time derivative of lambda. Okay. Then I have minus time derivative of A. So I will take the gradient out, so it will be minus gradient and phi plus the time derivative of A. Sorry, the time derivative of lambda, the arbitrary function that I had, minus time derivative of A. So in order to have electric field to not be changed upon changing A to be A plus lambda, then I have to choose that one as a new potential for myself. So the result is that now I would say that if you change A to be A plus lambda, also you have to change phi to be phi plus time derivative of lambda. Okay, that should be your new phi. Okay, is that clear now? So now I can conclude it in this way. Electric field and magnetic induction, they are invariant upon the following change of scalar and vector potential. So what are those changes? When you change A to be A plus gradient of lambda, which lambda is a function of x, y, and z. And on the other side, phi also is changing to be the time derivative of lambda. Okay. Upon this change of scalar and vector potential, electric field and magnetic field will not change. And now there will be another question. Will lambda be unique? Be unique? The question, the result is that no. So lambda should have a certain form. Yes, lambda is a scalar function because I'm taking the gradient, right? So it's a gradient of a scalar function. Well, thank you very much. Someone corrected me and say that it should be also function of the time because it should be taking the derivative with respect to time. Yes, that's perfectly correct. I hope that now is clear. So if you deal with a scalar and vector potential, that is the formalism that you are dealing with. And of course, I didn't talk about the Lorentz gauge or radiation gauge. Is something that you can look into that by yourself. So there is a relationship between A and phi as well, which either you choose the divergence of A to be equal to 0, or you choose the divergence of A to be equal to minus mu 0 epsilon 0 time derivative of the potential, scalar potential. Those are the choices that you may have. Even you may have other gauges as well. Excuse me. So well, that's the story. Now we will go to the curvilinear space, which we stopped there last time. Just to review, we say that we are working in Cartesian coordinate, in the Cartesian coordinates. We had x, y, and z, and now we are moving to any arbitrary coordinate. I mean, any arbitrary that we may design is up to you guys. I mean, you may choose x squared minus y squared is equal to a constant, xy is equal to another constant, and z is fixed, is one coordinate. You may say that x squared plus y squared is a constant, or is one of the parameter. Arctan of y divided by x is another one, and then you choose z to be a constant, so that's another parameter. So in curvilinear coordinates, as we discussed, you have new parameters of q1, q2, and q3. And know that next week I will generalize it. I will go even with the differential form. I will go with the manifold, and also I will go also with an arbitrary situation, which I will introduce the what do we call it, the covariant form, and also the dual space. So this lecture and tomorrow's lecture will be about the tensors. So I will not generalize it to any space, which yesterday also some of students, they asked questions related to whether this metric is associated to only the geometry, and I say no, it depends on also on the space that you introduce. It can be even for the polynomials. So let's go back to these questions. So Q1 and Q2 and Q3, they are the three parameters which there will be mapping between the two, okay, between the Cartesian and the curvilinear space that I'm working with. So indeed, what means is that X can be explained or expanded in terms of Q1, Q2, and Q3, and Y as well can be expanded in terms of Q1, Q2, and Q3, as well as Z, Q1, Q2, and Q3. And vice versa, also Q1, Q2, and Q3 also can be expanded in terms of X, Y, and Z, okay? Well, for sure here I have 3 unit vector of X hat y hat and z hat, they form a right angle as well. So it's like this: x hat, y hat, and z hat. They are unit vectors, and as we discussed, the nice property of the Cartesian coordinate, which is the simplest case, is that excuse me, when you move around these x hat, y hat, and z hat, they are fixed in magnitude and direction as well. In the same fashion, here I can introduce q1 hat, q2 hat, and q3 hat, which they are also unit vector. So I will go in an arbitrary situation, q1, q2, and q3, they form the right angle, but the magnitude is fixed, is a unit vector. But on the other side, when you move around, the orientation of q1, q2, and q3 can change. We made an example last time. Now we say that, well, what I'm interested in is that, assuming that I have a Cartesian coordinate, which we described, x, y, and z, and I do infinitely small displacement here along x, which I call it dx, infinitely small displacement around y, which I will call it dy, and infinitely small around z, which I call it dz. Okay. And now I am interested in the length change, which is changing from here to here, which I call it dr. And dr square is given by dx power of 2 plus dy power of 2 plus dz power of 2. Okay. I think we had no question in the past related to this. And here, after, since I'm using the summation notation, I would prefer that you, instead of using x, I will use x1. Instead of y, I use x2. Instead of z, I use x3. So indeed, that can be written as a dx1 power of 2 plus d1 dx2 power of 2 plus dx3 power of 2. So in a simple notation, that is look like the summation of I changing from 1 to 3 of dxi dxi, or for short, you can write it as dxi power of 2. Remember, you will see in maybe in 1 hour that everything gets so complicated that whenever I go with a power of 2, okay, or power of any number, I will write it as a parenthesis. Parenthesis of n means that is a power of n. But you will see, just be patient. So, and we say, okay, any of those x, x1, x2, and x3, if I take the derivative, so indeed, xi is a function of q1, q2, and q3. Well, I can easily call it I don't know, let's call it for sure, I will call it qj. Now I will ask what is going on with the changes in dx. So definitely that will be the derivative of xi with respect to qj, dqj. Okay. Or if you want to call this, let's go with a different notation because I will be needing it for different things, just to be consistent with what I had in the previous time. Okay, qi. So, well, and that means that I have summation on qi, which means that I have a summation on I changing from 1 to 3. So dr square is indeed equal to summation on I dxi dxi, or I can write it, summation is not important, the index, it can be k dxk dxk. And now I will replace dxk with the value that I have it here. So that will be summation on k. And then I have the derivative of xk with respect to qi, dqi, and there is a summation on I. The second one, as I say, I'm not using the index of I, because if I write this, the summation will be mixed up. So it should be a new summation of j, because it doesn't matter here. I can write also j, and j and j is the same. So it will be derivative of xk. What is important that the k is fixed. Derivative of q j dqj. While I will simplify the product, it will be the summation on I, j, and the summation on k, which is important. And then I will take the derivative of xk with respect to qi, derivative of xk with respect to qj, and then I have dqi, dqj. Remember why I take the dqi, dqj out of this, because the summation, this summation is over k, while the other two summations are on the qi and qj. So whatever happens with this quantity, that will be independent of index k, because I'm summing up over k, but the freedom that I have is on qi and qj, so it means that that can be written as a function of I and j. So indeed, that will be the summation on gij, dqi, dqj. And that's the summation on I and j. And as we discussed, we call these the metric of this space, which the metric metrics of the Riemannian space, the metric definitely depends on the form that you built up qi, q1, q2, and q3. In the Q&A yesterday, we discussed about that briefly, how to build up this. Okay. Now, we say that, well, this function is symmetric. If I have to be careful, I'm not saying yes yet. It is a tensor, and this tensor is symmetric. What does it mean? That jij is equal to ji. So, and we prove this. We say that you can swap the two and still is identical results. And we say for orthogonal space means that Q1, Q2, and Q3, they are mutually orthogonal to each other, then this metric will be simplified. And the result of this will be dr squared. We say that you don't have off diagonal term, you have only diagonal terms. So you have G11, G22, G33, and that will be the result will be G11 d Q1 power of 2, G22 dQ2 power of 2, G33 dQ3 power of 2. And myself, I will introduce G1 or GII to be equal to HI power of 2. And I call these the factors of the coordinate. So if you remember, I say that Gij, the tensor, is given by G11, G22, G33, and since it's symmetric is G12, G13, G23, and definitely that one also would be G12, that one will be G13, and that one will be G23. So they are identical. Okay, and now I'm talking a specific metric which which they are orthogonal, then Gij essentially is given by H1, H2, and H3 power of 2. Okay. So the result of this will be indeed H1 dQ1 power of 2, H2 dQ2 power of 2, plus H3 dQ3 power of 2. Okay. Questions? Lovely. So that is the scenario that I have. What I measured so far is what is happening with the distance in that space. I had the Cartesian coordinate, and I say that the distance is given by dx squared, dy squared, dz squared. And the same distance, I will explain it in another coordinate. I have a maybe spherical coordinate. What is happening with the dr squared in terms of d rho square, d rho, d theta, d phi, or in cylindrical coordinate, d rho, d theta, and also dz, or any coordinates. It can be du, dv, d phi. So what is happening with the relationship between the two? So, and we only concentrate on one specific, the coordinate which they're orthogonal coordinates. So it means that the unit vectors, they are changing in space, but always they are orthogonal to each other. In that space, as I say, the metric is diagonalized. So what is happening, that Gij is only, you have only the diagonal term. You don't have an off-diagonal term, because the off-diagonal terms, they are given somehow by the dot product of the two vectors. Good. And just to having a feeling how this is given by the dot product, because also that was a question that was asked yesterday. So look at the metric. So metric is given, Gij is given in terms of K, derivative of K with respect to Q1 or Qi, xk with respect to Qj. And what's that? It seems that I have taken two vectors and I have done the dot product because this index is repeated. Okay, well, let's write it in a different color. K index is repeated here. So, well, fantastic. If you write it down, that is look like derivative of x with respect to Qi or x1, derivative of x1 with respect to Qj, plus derivative of x2 with respect to Qi, derivative of x2 with respect to Qj, plus derivative of x3 with respect to Qi, derivative of x3 with respect to Qj. Well, I can write it in terms of y and x, y, and z. You will have a feeling, a better feeling. Can you tell me what's that? I'm looking at the Q&A. Can I write it as Qi dot R Qj? Can I write it in this way? Is a dot product of derivative of R with respect to Qi, derivative of R with respect to Qj. Do you agree on this? Yes, okay. Shao says yes. So anyone else? Do you agree with this conclusion? because R is given by X hat plus Y hat plus Z hat. Okay. Then if you take the derivative with respect to R of Qi, that will be derivative of X Qi X hat, because X hat is constant, derivative of Y Qi, derivative of Z Qi, that is Y hat, and also Z hat. And the same things happens with the derivative of R with respect to Qj is the same. And if you do the dot product between these two, what you will get these terms. Okay, so lovely. And what is the meaning of R, derivative of R with respect to Qi? So R, of course, is a vector in a space, and of course can be function of Qi. When you take derivative of R with respect to Qi, what you do, indeed, you are taking a vector and you look at the infinitely small displacement of that with respect to Qi. What does it mean? That you will find a tangent vector of the Qi. Okay. So you will find out what is happening with the unit, not really necessarily unit vector, but you will find out what is happening with the vector which is oriented along the Qi. So it's somehow that is proportional to the Qi. If you do the same for R respect to Qj, that's the way that you will find out. Well, just to tell you, in a basic way, if you have let's say a plot, okay, is a function. When you take a derivative, what do you mean? You will find out the slope there, right? The slope with respect to y respect to x, right? So this is what you will find out. And here is the same. You will find out the slope with respect to the change of the Qi. So it means that you will find out the tangent here. Okay, so you will find out the Qi vector. And the same things happens for the other one. You will find out the tangent vector with when you change the Qj. So that can be Q1, the other one can be Q2. And when you do the dot product, this is somehow, I wouldn't say that it is identical, but somehow is proportional to Qi that Qj. Okay, there is a coefficient at the front of that. And that's the reason that I say that when you assume that Qi is orthogonal to the Qj, that Gij will be equal to 0. So the off-diagonal term, for example, doesn't exist. But it may happen in a space that your space is not built up based on orthogonal vectors. For example, in the crystals, that the form of the crystal is different. I mean, the blocks that you have, the building blocks of the crystal may be different. Then not necessarily you will have the Qi that Qj to be equal to 0. Then the metric that you have it for that space, it has off-diagonal term. Okay.
Victor, sorry. Apologize. Yes. We have some question.
Yes, please go ahead.
Netiruan asked G sub I Ji equal to H square II is that because we still not specified the space.
No, I have not specified the space, Netiruan. The only things that I have chosen here is that space is built up based on orthogonal vectors. It's based on a Qi, let's say Qi, Qj, Qk, which they are orthogonal to each other. So Q1, Q2, Q3, they are orthogonal to each other. That's the only condition that I have, but I have not specified the coordinate yet.
Yes. And Muhammad Isa asked the Hi if Qij are orthogonal, what is the merit of new metric to delta S true?
Well, there are many coordinates which they are orthogonal to each other. So I mean, the unit vectors are orthogonal to each other, but they are not Cartesian coordinates. I will introduce a couple of them today, and then you will be using them in solving some physics problem.
Yes, and Manda asked, could you please give physical interpretation of whatever you have just now done?
Yes, I will do that. I will go with one of the examples. If you give me the time to drive the gradient and driving divergence and curl, then I will go with some physical examples.
Okay, and the last one, Mohammed Saeed asked, can you generalize this for more than 3 dimensions?
Absolutely, you can expand it to n-dimensional space, indeed. Okay.
Thank you.
Of course.
That's all question that we have so far.
Lovely. So, well, just having a feeling and a meaning about the metrics, it tells you how this transformation is happening, okay? And how these unit vectors, they are formed in the space. So in general, in that space of Qi, which I said, which means that is Q1, Q2, and Q3, then I have three orthogonal vectors. Remember, these three, they are mutually orthogonal. Okay, so it means that the metric that I have, Gij, only has the diagonal term. So h1 power of 2, h2 power of 2, h3 power of 2. And of course, if it's n dimension, I can go to, hn power of 2. Good. And in that specific space, any vector that you give it to me, A, can be written as A1, Q1, A2, Q2, A3, Q3. Okay? If you give me any vectors, I can write it in this form. Not necessary that all of them, they exist. So it may be 0, for example, as all other vectors that we know very well. If you give me another vector of B, the same situation happens. B1, Q1, B2, Q2, and B3, Q3. And now I'm asking you, well, what happens with A dot B? I will be using exactly the same expression that we know previously. So it means that I will take the A that I have, A1, Q1, plus A2, Q2, plus A3, Q3, and I will do the dot product of B1, Q1, B2, Q2, and B3, Q3. And if you do the dot product, Q1 dot Q1 is equal to 1 because it's a unit vector. Q1 dot Q2 is orthogonal space, is equal to 0. So the result will be A1, B1, plus A2, B2, plus A3, B3. Is that clear? So essentially, I can write it as summation of AI, VI, I is changing from 1 to 3. So it doesn't matter. The dot product that we introduced is still valid here and is working and having no problem. If it's not orthogonal space, so Q1, Q2, Q3, they are not orthogonal to each other, then I cannot write it as A1, B1, A2, B2, A3, B3. I have to do the entire product, and I have the explanation for that. Okay? It's clear. Good. Wonderful. So what is happening with A cross B? Again, in the same way, they form the right angle. And if you write the A cross B, I will get exactly the same way. Q1, Q2, Q3, A1, A2, A3, B1, B2, and B3. Exactly look like the Cartesian coordinate that we expanded and we used the determinant. So Q1 will be A2, B3 minus A3, B2. And the other one will be minus Q2, A1, B3 minus A3, B1 plus Q3, which is A1, B2 minus A2, B1. Or simply, because I know that some of you got confused last time, we have A2, B3 minus A3, B2 plus Q2, A3, B1 minus A1, B3 plus Q3, A1, B1 minus A2, B2. Okay.
Professor, we have
Yes.
3 questions. If you
Yes,
want,
please.
I can read for you.
Yes, please go ahead.
Yes. Mohammed Isa asked, is there any measure to specify orthogonality of Gij without direct calculations?
This is exactly what I explained previously. I say that, well, Gij, I have written here, right? So I say that Gij is given by the normal vector in the direction of Qi and normal vector in the direction of the Qj, and that is look like Qi dot Qj. So this is what I explained. This is without calculation.
Yes. And Subra asked, please explain the dot and cross products of non-orthogonal coordinates.
Wait for it. Wait for it. Yes, the good, very good question, because that requires a lot of calculation. Okay.
Okay. And Amir Hosseini asked, will the dot or cross product change in value of by changing the coordinate, for example, by going from Cartesian to spherical?
No, the dot product will not change for sure. Okay, and the cross product, if there are two vectors in a space, yes, does not change at all. Okay. The result you will see when it comes back to this, the result is a vector with the same property.
Yes. And last question, the last term of the cross product is A1, B2.
Yeah. It's A1 and B2. Yes, of course, because I have written here. So as a type. Thank you very much, Mohammed. Well, that was about dot and cross. Remember, that's not for a Cartesian coordinate. That's again for orthogonal arbitrary coordinates of Q1, Q2, and Q3. Okay, so now I'm asking, well, what is happening with the dr? Okay, so we say that if you have a dr dot dr, as we describe here, that will be equal to in the previous example. I mean, if you look at this example here, which we did a calculation, that is equal to h1 dq1 power of 2 plus h2 dq2 power of 2 h3 dq3 power of 2. So, well, this is look like h1 dq1 h1 dq1 and the same H2 dQ2, H2 dQ2 plus H3 dQ3, excuse me, H3 dQ3, and that is look like the first element that you have it for dr in the coordinate of Q1, Q2, and Q3. So that is look like H1 dQ1 in the direction of Q1 and H2 dQ2 Q2 plus H3 dQ3 Q3. So with this, also I find what is happening with infinity small displacement of R. So in the Cartesian coordinate, remember that was dr is equal to dx x hat plus dy y hat plus dz z hat. What is the dimension of this? Is meter is what? Can you type it in the Q&A? What is the dimension of dx, dy, and dz, if that's a displacement? Dimension is length, exactly, is meter. So the dimension of this is meter, means that it's length, and is length, okay? What is happening with the dimension of, I mean, in the arbitrary coordinate that we work with? So we have Q1, Q2, and Q3. What is happening with the dimension of dQ1, dQ2, dQ3? What is the dimension of these? It can be any arbitrary coordinate. Can you type in the Q&A? Mobin says that depends on h, length square. Okay. What else? Any thoughts? We know that HDQ is exactly. Mobin says perfectly. What is important here? That H1 dQ1 has the dimension of meter, is a length. H2 dQ2 is has the dimension of length as well, and that one also. But we don't know about dQ2, 3, and 1. We have absolutely no idea at this moment. But what is important that each of them, which H1, dQ1, H2, dQ2, H3, dQ3, they have the dimension of the length. Okay? So that is something very, very important. I'm not giving you example at this stage, because I will go with two examples at the end. So so far what I'm doing, I'm building up the elements that I'm doing the calculus with it, but in any arbitrary orthogonal space, or curvilinear space, curvilinear orthogonal space. Well, I know the dot product, I know the cross product. Now I calculated what is happening with the element of displacement, which was H1 dQ1, Q1, and H2 dQ2, Q2, and H3 dQ3, Q3. So now the question is that, well, I want to do the calculation of the integral. So how should we do the integral calculation? Well, I have integral of a scalar function of Q1, Q2, and Q3, and I will do dr, right? This is one of the integrals that I have. The other integral that I have an arbitrary vector of A, which is a function of Q1, Q2, and Q3. I will do the dot product with R. Do you agree? I will do also A, Q1, Q2, Q3, cross product of dr. So these are the three integrals that I may face. Let's go with the first one. The first one is easy. What you need to do, you replace dr with whatever we have it here. So it becomes 3 integrals on Q1, Q2, and Q3, okay? So that will be integral of phi Q1, Q2, Q3. Then I have H1 dQ1, Q1, and phi Q1, Q2, and Q3, H2 dQ2, Q hat 2, plus the other term, which is the last term. Okay? What about the second one? How do you write it? It's A, which has a A1, A2, A3, dot product with Q, dr. So it will be A, which is A1, Q1, plus A2, Q2, plus A3, Q3. Since they are orthogonal, Q1, Q2, and Q3, then easily that will be given by A1, H1, dQ1, plus A2, H2, dQ2, plus A3, H3, dQ3. Exactly, sum of AI, HI, DQI. Lovely. So as Amir Hossein said, so let's write it in that form. So it will be I, AI, HI, DQI. Lovely. And I is changing from 1 to 3. What about the third integral? Well, guys, recall, I have not yet discussed this and that one, okay? I have just expanded the form. Now, look at the third integral. How do you write it down? I have to write it down as integral of Q1, Q2, Q3. Then I have A1, A2, A3. And then here I have H1 dQ1, H2 dQ2, H3 dQ3. So indeed, the result of this will be integral of Q1, A1, no, sorry, A2, H3 dQ3 minus A3 H2 dQ2 plus the Q3 Q2 A3 H2 dQ2 minus A2 H3 dQ3 plus the other term. Okay, so I have expanded these. So yes, you can write it also in terms of Levi-Cita notation. So it's perfectly fine. Now look at the first integral again. Take this first integral. Is the most tricky part. I would say that is the first and the last integral. Oh, yes, of course, Shubra. I mentioned that. Well, I say that it's proportional. I didn't say that is a dot product. Look at this coefficient that I had it. I say that is proportional to the tangent vector. I didn't say that is identical. Is that clear, Shubra? Yes, but whenever the Qn and the Qj, they are still orthogonal. I mean, this is what we assume, that when we assume that they are orthogonal to each other, that's what happens. That the Qn and the Qj, they will be equal to 0. Well, maybe at the end of the lecture you can take the microphone and tell me. Okay, is that okay?
Sir,
Yes.
sir, right, our vector QK, then it is what in some terms okay.
I cannot hear you at all, unfortunately. I don't know if it's me or is all panelists.
I think his internet is unstable, I think.
Subra, would you please, is it possible if you find a stable internet and asking the question at the end of the lecture? Is that okay? Okay, perfect. Thank you. So going back to this question, so the first integral, look at the first integral. I will write it down. So let's go with the first integral, which is the integral of phi of Q1, Q2, and Q3, H1, dQ1, and Q1, okay? And then I have another three integrals similar to that one. I have a phi of Q1, Q2, and Q3, H2, dQ2, and Q2, plus integral of phi of Q1, Q2, and Q3, H3, dQ3, Q3. In the past, what we have done, we say, okay, easy. So I will take the Q1 out of this integral. Okay, I will take it out because it's a constant, and I will do the integration, and very likely also H1 will be a constant. This is not true here. Q1, it is a unit vector, but also it is function of, it is a function of position, which can be a function of Q1, Q2, and Q3. Okay, that's very important. So you cannot take it out in general out of the integral. So you have to keep it inside of the integral. What about H1? The same story. So H1 also can be a function of Q1, Q2, and Q3. So in a short, what I have to write, let me see, someone's microphone is on. Okay, so I have to write it down as integral of H1, which is maybe it is, in general, is a function of Q1, Q2, and Q3, Q1, Q2, and Q3. And then I have a phi of Q1, Q2, and Q3. I have to be careful about the Q1, which can be a function of Q1, Q2, and Q3. That, remember, that's a unit vector. And then I have the Q1. Okay, for sure, I will write that as integral of H1 phi Q hat 1 dQ1. So the difference with the Cartesian coordinate is that in the Cartesian coordinate, easily I will take the x hat out of these. There is no H1, H1 is equal to 1. And in the Cartesian coordinate, that will be simply given by phi dx. Okay, but here I have to be careful with H1. I have to be very careful with Q1 as well. And the same story, it's true for H2 and Q2, for H3 and Q3. Okay, so that is the importance of using curvilinear space, okay, or coordinates. The same story is true for integral number 3 as well. For integral number 3, you have a Q1, you have H2, you have H3, you have Q2, H2, H3, And also you have Q3, which I have not written here. You have also H1 and also H2 in the calculation, which they are not constant, and you have to handle it properly for any different coordinate that you deal with. The only integral that is easy to handle is the second integral, which is the dot product. So integral of A dot dr, which we have written as a summation of I integral of hi ai dqi. And here also hi is a function of, in general, q1, q2, and q3. Okay, so that is something that I have to be careful. Questions so far? No question? So from the integral on the length, now I'm moving to integral on the surface, okay? So what happens with the surface? Let's look at the surface. So if you remember, in the previous example of the Cartesian coordinate, we say, well, I have a surface here. I will move in the direction of x. I have these dx. I move in the direction of, I move in the direction of y. Oh, sorry, that's a dx and the other one is a dy. My apologies. That's x, y, and that is z. So this is y hat. This is dx x hat. So I built up a small region here. If you zoom in, I built up a small region here, which this small region will create me a surface here. So, and then I would say that what is happening with the unit vector of the space, this surface, this is essentially given by dx, dy, and the direction is given by right-hand rules. It will be along the z direction. So it will be along z hat. Okay. So that is dx x hat. That is dy y hat. And the result will be given by that. Okay. Now the same situation in an arbitrary coordinate. Let's call it this arbitrary coordinate like that. So I will plot it in a strange way. This is the arbitrary coordinate that I have. Is a q1, q2, and q3. So, well, I will only zoom on these. So now I'm asking you, what is happening with the dq1? Is this dq1 that is a dq1 q hat? Is that correct, guys? Is the element of the length?
Victor, there's a question, if I may read it for you.
Well, I will answer to the question later on. Let's go with this. Okay. No. Okay, good. What I need, Mason. Shania, what I need. Exactly. I need H1 as well. And that will be the element of the length. And here I will have also H2 dQ2, and then I have a Q2 hat. And the length that I will create here and the surface that I will create here, since Q1 and Q2, they are orthogonal to each other, and also they form a right angle with the Q3, then the surface that I will create here will be H1, H2, dQ1, dQ2 along the Q3 direction. Okay. So here, what I want to say to you, you may have several different surfaces. One surface along Q hat, Q1, one surface along Q2, one surface along the Q3. Okay, so indeed, I'm expecting to have the element of the surface, the infinitely small d sigma, I would expect that I have d sigma, write it in this way, sorry, q1 d sigma 1, which d sigma 1 is created by infinitely small displacement on the direction of the dq2 and dq3. So that will be equal to h2, h3, dq2, dq3. Look like what I have derived here. What I have derived here, that is for the element on the direction of the q hat, q3, sorry. And then I have q2 d sigma 2 plus the q3 d sigma 3. So that will be equal to, if I write it down, it will be h2, h3, dq2, dq3 along q1 hat. The other one will be along q2 hat, which will be h3, h1, dq3, dq1 plus q3, h1, h2, dq3, dq2, or dq1, dq3. Okay. So that is the element on the surface that I needed to introduce the other vectors calculation. So what I can do, again, I can have a scalar of function of q1, q2, and q3, then doing the dot product and doing the integration on the surface, or I can have a vector that d sigma, or I can have a vector doing the cross with d sigma. Okay, I will introduce all of them. So you can do the calculation, and you know very well that also the q1, q2, and q3 in general, they are not constant with respect to q1, q2, q3. So you have to keep them inside of the integral. So the result of these will be integral of phi h2, h3, dq2, dq3, and also you have a q1. Remember, now the integration is not on one parameter, the integration will be on the two parameters of dq3. And the same for the other one, which will be integral of phi h1, h3, dq1, dq3, and then you have a q2, and finally you will have integral of phi h1, h2, dq1, dq2, and you have a q3 hat. The second one, you have a1, q1, a2, q2, a3, q3, and you do the dot product, and the result of these will be a1, h2, h3, dq2, dq3 is a scalar quantity, plus the integral of a2, h1, h1, h3, dq3, dq1, and finally integral of a3, h1, h2, dq1, dq2. And in a similar fashion also, you can exactly do the calculation for the last one. So it will be integral of q1, q2, q3, the unit vectors, and then you have a1, a2, a3, and for the d sigma, you have to be careful now. You have h2, h3, dq2, dq3, and for that one, you will have h1, h3, dq1, dq3. And finally, for the last one, you have h1, h2, dq1, dq2. And you do the calculation, and you will see, you will get a vector integral, okay? That's also important. And finally, the last one is integral on a volume. So you want to build up a volume. how did we do or we created the volume? So you had a point in a space, you did displacement in dx, you did the displacement in dy, you had the displacement in dz. So that was dx, dy, and dz, and you built up a cube based on that small displacement here. And the volume that you had it d tau was dx, dy, and dz. Here we will go with our coordinate, the coordinate that I introduced last time. I say that you have these q1, q2, and q3, which they are changing in space as well. Then how to build up a volume, I move it in the direction of dq1. So the length was given by h1 dq1, and then that one was h2 dq2, and here the height was also h3 dq3. So the volume that we created here was given by the length of all direction multiplying together, because it's orthogonal to each other. So the d tau here is given by h1, h2, h3, dq1, dq2, dq3. Exactly. All of you got it in a proper way, Mohammed and other people in the room. So wonderful. So the element of volume for this curvilinear space, orthogonal one, is h1, h2, h3, and then you have a dq1, dq2, and dq3. Remember, h1, h2, and h3, they are not constant. They are the scaling factor or the parameters that we are dealing with. So how many integrals do we have? We have integral of phi of q1, q2, and q3. Then integrating it on a volume, or you may have a vector integrating on a volume. You may have a vector. That's it. You don't have something else. So, and then the result of this will be equal to integrating of phi h1, h2, and h3, dq1, dq2, and dq3. And the last one will be integrating of a1, h1, h2, h3, and you have a q1, okay? And then we have a dq1, dq2, dq3, and the same for the other one, which will be a2, h1, h2, and h3, q hat 2, dq1, dq2, dq3. And we have also integrating of a3, h1, h2, h3, q hat 3, dq, dq1, dq2, dq3. Lovely. I think we are so far good, and now we know how to do the integration, how to do also the integration not only on a line but also on a surface in these general coordinate and also on a volume.
Professor, sorry, there are two questions, if I may.
Sure.
So the first question from Amir Hussein is, he says, doesn't the orthogonality condition mean that Q1 and Q2 and etc. are independent? Then how does Q1 power depend on Q2 or Q3?
Oh, you will see that that is not true, Amir Hussein. So, well, of course, they are independent, right? So we say that Q1, Q2, and Q3, they are independent parameters, right? But as an example, assume that you have a Cartesian coordinate, right? Well, x hat, y hat, and z hat. Well, perfectly. These are the three vectors which they are constant in space and if you and also in magnitude and direction. Now assume that you are dealing with a cylindrical coordinate, a spherical coordinate. So that's the r hat, right? Is one of the vectors. And then now I'm changing r hat. When we talk about it, we have three parameters of r, the distance from the sphere, the origin of the sphere, And then we have the orientation, which is a phi, and then we have the angle from the North Pole, which is the theta. Then I'm moving r hat, I'm pointing somewhere else. And you will see that r hat is moving as well. So r hat is not constant with respect to Q2 and Q3, which is they are theta and phi. Okay. So in general, they can be a function of Q2 and Q3. Okay.
So thank you, Professor. And the second question is from an anonymous attendee. He says, can you please give an example on an integration the vector vec q1, q2, q3 over its component?
Oh, yes. I said that I will give an example in a few minutes. Yeah.
Mhm. Thank you. And the third question is H1, H2, H3 is Jacobian, right?
We can go with definition of the Jacobian as well. I mean, it's really up to you. If you want to, guys, you can also explain in terms of the Jacobian. Yes, for the surface and for the volume, all can go in terms of the Jacobian. Okay.
So, Professor, the last question is from Shania.
Okay.
She says, can we use closed surface integral of A, Q1, Q2, Q3 to find volume integral?
Oh, you can do that. Yes. Yeah. Absolutely not a problem. Whatever we discuss is valid.
That was all. Thank you, Professor.
Okay, of course. Of course. I mean, one of the students talked about the Jacobian. Okay, so let's look at the Jacobian. By the way, I have to drive the gradient divergence and also the curl in that space, but I think the Jacobian matter is important. So well, look at the displacement that we may have in the Cartesian coordinate. You may have a dx and you may have a dy, and as we described, then you have an element of the surface which is dx dy in that direction, which is the direction of the z hat, right? Well, how do we build up this? We say, okay, take the dr. I mean, you have r, which is x hat plus y hat plus z hat, right? And then what I will do, I know that r is a function of, sorry, I'm giving an example in terms of Cartesian coordinate because it's very easier to handle. So I'm looking at the change of r with respect to the x parameter, with respect to this parameter, and with respect to the second time I will with respect to y parameter. So let's do this. So what I will do, I will take the dr when x is changing only. Okay. Then what I will get dx, right? Do you agree with me? So it will be r of x plus dx and y and z minus r of x, y, and z. Beautiful. Any problem with that? I don't think so. So then what we will get derivative of r with respect to x dot dx. What is happening when we do the calculation also with the dr when y is changing? Then I will have exactly the same expression, dy. Good. So what I'm doing right now, I'm building up this vector and this vector when they are changing. Okay. Now I look at the surface that I have it here. So dr I can simplify further. Derivative of r with respect to x, derivative of r with respect to x, what you will get? You will get x hat dx, and derivative of r with respect to y, what you will get? You will get y hat dy. Good? Yes, this is an approximation, of course. is an approximation because I'm changing at infinity small, and then dx is asymptotically going to be 0. Okay, so well, this is what happens when I will change the dr when I'm changing x to x plus dx and y to y plus dy. And then what I will build up these two vectors. And now I'm asking what is going on with the surface. Okay, these infinity small surface, so the element of the surface, is given by, I will call these dr1 because I'm changing x. And I look at the dr2, which is that one. Then I will do the cross product of the two, and I will find out the element of the surface. Now let's do the calculation. You will get is x hat dx cross product of y hat dy. And the result of these will be dx dy x hat cross y hat, which is equal to z hat. Okay? So this is the way that we find the element of the surface. Agreed? All? If you agree, let's do the same thing for not a Cartesian coordinate, but going with a curvilinear space coordinates of Q1, Q2, and Q3. So what does it mean that R, here R that we have is given by, in general, is given by a function of Q1, Q2, and Q3. And then what I will do, I will change in the direction of Q1 and the direction of the Q2. And I want to find out what is going on with the length here, what is going on with the length there. So if you do the changes, dr, when Q1 is changing, when Q1 is changed, then means that I have R of Q1 plus dQ1 and Q2 and Q3 minus R of Q1, Q2, and Q3, when of course the Q1, dQ1 asymptotically going to be 0. And then the result of these will be the derivative of R with respect to Q1 multiplied by dQ1. And I can do the same thing for the dr when Q2 is changing. In the same fashion, I will get the derivative of R with respect to Q2 dQ2. Do you agree? Now I'm asking what is happening with the element of the surface. An element of the surface is given by the first one, which I will call it dr1. This one I will call it dr1. And the second one I will call it dr2 because the second parameter is changing. Multiplied by dr2, that will be the element of the surface. So indeed, the result of this will be derivative of R with respect to Q1 dQ1 cross product of derivative of R with respect to Q2 of dQ2. Okay? Good? So that means that I have a dQ1, dQ2, and then I have a derivative of R with respect to Q1, cross product of R with respect to Q2. What's that? Exactly. It is called the Jacobian term. So if you do the calculation, because what I'm looking for indeed, that will be along the Z direction. And if I look at the Z direction of this, right, because that is in the XY plane, XY plane, then I'm looking for the Z component of these, that will be dQ1, dQ2. And then if you look at for the Z component of that, that will be a derivative of X with respect to Q1, derivative of Y with respect to Q2, minus derivative of y with respect to Q1, derivative of x with respect to Q2. Okay. And that term is indeed look like the determinant that I have dq1, dq2, and that is nothing more than derivative of x with respect to Q1, derivative of y with respect to Q2, and then I have a derivative of y with respect to Q1, derivative of x with respect to Q2. So that is exactly the Jacobian that was mentioned by one of the attendees today. Good, so far, so good, not a problem. Now let's go and find out what is happening with the three main derivatives that we were dealing with. So the first one, we built up dr, which was h1 dq1 yes, this is what we have done, which is you will see. Still, Rupesh, I got your question, but yeah, I'm not yet doing the calculation, so I will tell you more. H2 dq2, and we have a q2 plus h3 dq3 and q3. Now, what I want to say, what is happening with the gradient of a scalar quantity? Of course, when we say the scalar quantity means that now the scalar quantity is a function of Q1, Q2, and Q3. What is happening with the divergence of a vector of A in that coordinate? What is happening with the curl of these in that coordinate? So these are the three main questions that right now we do have, and we have to handle it properly. So the gradient of phi, what is happening with the d phi? If you take a d phi, well, phi is a function of Q1, Q2, and Q3, then that can be expanded, is a derivative of phi with respect to Q1, dq1, derivative of phi with respect to Q2, dq2, plus derivative of phi with respect to Q3, dq3. Well, the gradient, if you recall, we say that the gradient is indeed, if you take any scalar function and you change it, then the result will be gradient dot dr. So I don't know the element of the gradient. I will call it, I don't know, let's move this here. So the component of the gradient for me is unknown, and I will call it, I don't know, G1Q1 plus G2Q2, sorry, plus G3, oh, I don't know, my brain doesn't work, plus G3Q3, okay? So, and now the question that I have, what is G2, G1, and G1, G2, and G3? So, and I know that dr is given here. So indeed, the dot product of these two, the result will be G1 H1 dq1 plus G2 H2 dq2 plus G3 H3 dq3. And comparing the two together, comparing this one and this one, assuming that based on the assumption that Q1, Q2, and Q3, they are independent parameters, then we definitely we come to the conclusion that the coefficient of these should be equal to the coefficient of that. And vice versa, and in the same fashion, G2 H2 should be equal to this coefficient, and finally the last term, this term, also will be the coefficient will be equal to that one. So the result of these will be that G1 H1 should be equal to derivative of phi with respect to Q1, and G2 H2 should be equal to derivative of phi with respect to Q2, and G3 H3 should be equal to derivative of phi with respect to Q3. So means that G1 is equal to 1 divided by H1 derivative of phi with respect to Q1. G2 is 1 divided by H2 derivative of phi with respect to Q2, and G3 is equal to 1 divided by H3 derivative of phi with respect to Q3. Right? Which is wonderful. So what was H1 dQ1? H1 dQ1. Do you remember? We say that that's infinitely small. Exactly. It's infinitely small in the direction of the dQ1. So I call it dR1. This is dR2. This is dR3. If you remember, this was the way that I built up the volume, I built up the surface. So indeed, that is somehow derivative of phi with respect to R1, derivative of phi with respect to R2, derivative of phi with respect to R3. So what does it mean that always the gradient, the unit of the gradient is 1 divided by length, and that's really an important factor. So from this calculation, what I will get, that gradient indeed can be defined in the orthogonal curvilinear coordinates. Is given by Q1 divided by H1 derivative with respect to Q1 plus Q2 divided by H2 derivative with respect to Q2 plus Q3 divided by H3 derivative with respect to Q3. Remember, again, I'm repeating myself, which is absolutely there is no problem at all. So Q1, Q2, and Q3, they are orthogonal to each other. Okay, and H1, H2, H3, they are square root of the diagonal elements of metric that we are dealing with. Okay, so in order, and that's a gradient. So remember that the gradient of phi is easy now, is given by Q1 hat H1, or some people even they write it in this way. So let's get familiar with this. So they write it as a 1 divided by H1 derivative of phi with respect to Q1, and then you have a Q1, 1 divided by H2 derivative of phi with respect to Q2, and then you have a Q2, and H1 divided by H3 derivative of phi with respect to Q3 and Q3. However, when it comes to divergence, you have to do the calculation properly. You cannot just take the gradient and doing the dot product and getting the result. So you have to be careful with that, and in order to do the divergence, to do the calculation of the divergence of a vector, you have to go with the integral formalism. So indeed, divergence was given, divergence of a vector on a volume, on a surface. A dot d sigma divided by the volume that we had in the limit of volume going to 0, then that will give you the divergence of the vector. This was the way that we calculated the divergence of A, and also the curl of A exactly in the same fashion we calculated on a loop. And if you do the calculation, it's a little bit, it's identical to what I have done in the past, but it's a little bit lengthy. I don't want to go through all of these calculations. So divergence of a vector of A, which now I'm writing in a Q1, Q2, and Q3 coordinate, which they are orthogonal, of course. And the result of these will be 1 divided by H1, H2, and H3. By the way, I don't memorize things, and I'm looking at what I have written just before the lecture. So it's a derivative with respect to Q1. And then you should have the first component, which is A1, and then you have H2 and H3, and then derivative with respect to Q2, then you have A2, it should be H3, H1, and finally you have a derivative with respect to Q3, and you have A3, H1, H2. Okay, so that's a divergence. Remember, that's again scalar quantity. Okay.
Thank you, Professor. Professor, there is a question that Subhra asked. Subhra says you have written form of differential of distance dr in a general curvilinear coordinates, but how do you write distance r in a curvilinear coordinates in general form?
So, you can still write the dr in the way that I have written, and the only difference that I have, I mean, this is what I started the calculation with. So, going back to here, so this was what I have done. I mean, if you look at the calculation, I started from this equation. Okay. And that's a general formalism. This is how do you write it in a general coordinate, indeed.
Thank you, Professor. And there's another question from Shaho. He asks why it's not possible to compute the divergence from the component y dot product of a nobla and A.
Well, you can introduce that way, but remember that the divergence is an operator, right? And if you write it just simply as the gradient that we had it here and that product with A, you don't have a proper scaling. You don't have a proper scaling. You have to go with the definition because it should have a meaning in physics, and the meaning was a flux that we had. So you have to really go with that definition because the integral on the surface plays a role.
Thank you. And Mahdi asks why scalar quantities?
Oh, because it's a divergence, it's dot product. It's a flux. Right? Do you see any vector here? I don't see any vector. Is the derivative with respect to Q, the Q1, Q2, Q3. There is no unit vectors in the calculation. Okay.
Thank you, Professor. That was all for now.
Okay, lovely. In a similar way that previously that we calculated the curl, you can also do the curl and calculate it from the integral formalism. And the curl will be given by 1 divided by H1, H2, H3, and then you will get it from the Q1, Q2, and Q3 with the proper scaling. Of course, you have H1, H2, and H3. Then the element of the curl, which will be derivative with respect to Q1, derivative with respect to Q2, derivative with respect to Q3, and then you have A1, A2, A3, and all of them, they should have the same metric. So this will be H1, H2, and H3. So that is the way that someone can calculate also the curl in a curvilinear space. Okay, so so far I think we have all the elements. I will encourage you in the same way that I proved for the Cartesian coordinate. In interest of the time, I can do it for you right away, but in interest of the time, I will encourage you to do the calculation for these. Okay, start from the right side, which is this one, and using the d sigma that previously I introduced, and do the calculation and drive the divergence of A. Do it once, and I'm sure that there is a little bit of fun that you have to be very careful. And note that H1, H2, and H3, they are not constant. In general, they are function of Q1, Q2, and Q3. That was the reason. Look at the notes and pay attention to which part of the function you are taking out of the integral, which part you cannot take out from the integral. So, so far, we introduced all of the elements that we needed for the orthogonal curvilinear space. So, and now I will go with a couple of examples just to tell you how these can be used in physics problem. So, well, let's go first with the Cartesian coordinate is easy. Let's go with the Cartesian. In the Cartesian coordinate, what is going on with Gij? Gij easily is 1, 1, 1. Okay, not a problem at all. How we are sure of this? Because if we calculate the d r squared, that will be dx squared plus dy squared plus dz squared. That means that h1 is equal to 1, h2 also is equal to 1, and h3 also is equal to 1. Okay, so that's easy. And from here, I can calculate the dr. dr again is given by, if you recall, h1 dq1, so it will be dx x hat plus dy y hat plus dz z hat. Okay, and look at the divergence. You can look at the gradient. So since h1, h2, and h3 they are equal to 1, you will get exactly all mathematics that we have previously proven. Let's go to another coordinate, and these coordinates. Let's go with I don't want to go with the Minkowski one. I will go with cylindrical coordinate. Cylindrical coordinate. So which is given by rho, phi, and z. Okay, and rho, as we previously say, is changing from 0 to infinity, plus infinity. Phi is a cyclic function, a cyclic parameter, so phi is between 0 and 2 pi. And z is changing from minus infinity to plus infinity. So just having an idea, that was rho. Oh, let's say that is rho. If you project it here, you will have an angle which I call it phi, and this distance is a z. The first thing, how do I write r? Okay, how can I find r? Can you type it for me? Should I write r as a rho hat plus phi hat? I'm asking a question. Plus z hat. Can I write this? Yes, right. Thank you. Yeah, some people they say yes, some people they say no. Yes, no, yes, no. Okay. So First of all, if I write it in this way, what is wrong? I will tell you, look at the physics. What is the dimension of this? Is length, right? What is the dimension of this? Is radian multiplied by a unit vector, has no dimension. What about this? Is length multiplied by 1 is length, okay? So indeed, this part is somehow doesn't have a proper unit. In the other way, well, we don't need that essentially. It has a problem, has a serious problem in the calculation. And let's do the mathematics and see what are the problems. I always encourage you guys to look at the Cartesian coordinate, because always helps you to understand if you are doing a wrong calculation or not. So x is given by rho cosine of phi. Do you remember? So if you project it on this direction, that is rho cosine of phi. About y is rho sine of phi. Okay. What about z? You will have z the same value. So y is rho sine of phi, and z I have z. Okay. So now in the Cartesian coordinate, I have x hat plus y hat plus z hat. Remember, this is exactly the expression that I say to you. X is expressed in terms of rho, phi, and z, in general, in z, okay? Y is expressed in terms of rho, phi, and z. And also here, z is expressed in terms of rho, phi, and z. Well, here we know that is only function of rho and phi. Here is rho and phi, and here is only z, but is a choice that we had in this specific example, okay? So r is given in the Cartesian coordinate, is given in this way. So I will replace x with rho cosine of phi, x hat plus rho sine of phi, z, my apologies, y hat plus z hat. Okay. This is r vector. In which coordinate, guys? This r vector is in Cartesian coordinate. Cartesian coordinates, but expanded in terms of cylindrical parameters, cylindrical coordinates parameters. It is expanded in terms of rho, phi, and z, but it's not explained in terms of rho hat, phi hat, and z hat. So the first thing from this is building up the unit vectors. The unit vectors. How do you build up a unit vectors? Can you type? Can you tell me? How did we find the slopes? Do you remember the tangents? We take r, and which is a function of q1, q2, and q3, which in this example is a function of rho, theta, and phi, and we take the derivative of r with respect to those parameters. So q1, that will be proportional to the q1 hat, and etc. Derivative with respect to r with respect to q3, that will be proportional to the q3 hat. So let's do this. So I have r, which is expanded in terms of rho cosine of phi x hat plus rho sine of phi hat. Sorry, my apologies. Y hat plus z hat, and now I will take derivative of r with respect to rho, which is the Q1. And what I should get something proportional to the Q1. So that will be equal to derivative of rho cosine of phi with respect to rho will be cosine of phi x hat plus sine of phi y hat, and derivative with respect to phi of rho of z is equal to 0. And this should be proportional to the Q1, which is equal to rho hat. So what I have to do, I have to normalize it as well. So then rho hat indeed is a cosine of phi x hat plus sine of phi y hat divided by the magnitude of these, which the magnitude will be cosine of phi power of 2 plus sine of phi power of 2, which is equal to 1. And then rho hat is a cosine of phi x hat plus sine of phi y hat. Y hat. Derivative of r with respect to phi. Take the derivative, that will be rho. Derivative of cosine will be minus sine of phi x hat plus derivative of sine will be cosine of phi y hat plus derivative of z with respect to phi, that will be equal to 0. So that is proportional to what we call it the Q2, or which is equal to phi hat. So phi hat is indeed equal to minus rho sine of phi x hat plus rho cosine of phi y hat divided by the magnitude of these, which will be minus rho sine of phi power of 2 plus rho cosine of phi power of 2, which is equal to rho, and the entire of these will be minus sine of phi x hat plus cosine of phi y hat. Derivative with respect to z of r, which will be simply equal to z hat, which is exactly proportional to the Q3, which is z hat. So in this specific example, z hat is equal to z hat. So the unit vectors in spherical coordinate, cylindrical coordinate for me, the Q1 hat is equal to rho hat, which is equal to cosine of phi in terms of the Cartesian coordinate, sine of phi of y hat, and Q2 hat is equal to phi hat, which is equal to minus sine of phi x hat plus cosine of phi y hat, and then Q3 is equal to z hat, which is z hat. Okay, so those are the three unit vectors that I have. What was r? R was given here, right? So r was given by rho cosine of phi x hat plus rho sine of phi y hat plus z hat. So you take rho out, then you will get cosine of phi x hat plus sine of phi y hat plus z hat. And this is nothing more than Q1, which is rho hat, and this is Q3, which is z hat. So indeed, r is given by rho hat plus z hat. Note that here, rho hat is a function of phi. Z hat is fixed. Is a one example that I have, which is everything is so beautiful, is wonderful. Okay. Now I'm asking, what is happening with dr? Okay. dr, you take the derivative of these, it will be d of rho hat plus z hat. What will be the result? Can you type it here? I will write something and tell me if it's correct or not. So if everything is going smooth, then that should be d rho hat, okay? And then I have dz z hat. Can you tell me if this is true or not? Mobin says he's wrong. No, this is not true. This is not true. Why this is not true? Can you tell me? Exactly. You correctly answered to the question. There is a missing term here, which this missing term comes from the fact that this rho also is a function, as we described, is a function of phi. Okay, so what I have to do, I have to take the derivative of two functions, so d rho hat plus rho d rho hat, which plus z dz z hat. So now I have to calculate d rho, okay? And well, the first term is easy. The last term also is easy, but this term, I have to calculate what is happening with the d of rho hat, which rho hat was, if you look at the equations that I had it here, this is the rho hat. So I have to take the derivative of cosine of phi x hat plus sine of phi y hat. So as we say that these are a function of rho phi indeed. So the result of this indeed will be equal to the derivative of cosine will be minus sine of phi x hat, and of course I have d phi, and the x is constant, x hat. The unit and the direction is constant, so nothing is changing. And the last term will be cosine of phi, d phi, and y hat. So I can factor out the d phi. I have minus sine of phi x hat plus cosine of phi y hat. What's that? This is equal to phi hat. Agreed? Exactly. So the result of dr indeed is equal to d rho hat rho d phi hat plus dz z hat. What's that? Do you remember that we say that dr is equal to h1 dq1 q hat, h2 dq2 q2 hat, h3 dq3 q3 hat. So what are those? This is dq1 h1, this is dh2 dq2, this is h3 dq3. So from here, immediately I will find out that h1 is equal to 1, h2 is equal to rho, and h3 is equal to 1. So Gij that I have is indeed equal to 1 rho 1. So that's a metric of the space that I have. So now I can ask you, what is happening with the d sigma? Okay, so I have 3 sigmas. One is a long rho hat, which is built up by phi and z. So that will be rho d phi and dz. Then I have the other one, which is the d rho dz phi hat, and then I have the last one, which is rho d phi d rho z hat. Okay. Well, I can build up what's going on with the gradient of a scalar that will be equal to, or let's call it psi, just to not get confused. That will be 1 divided by h1. If you remember, derivative of q1 of psi of qi. Let's go with a short notation. And if you do the calculation, that will be a derivative with respect to rho of psi of rho hat, 1 divided by rho of derivative with respect to phi of psi of phi hat, plus derivative with respect to z of psi of z hat. Okay, that was a gradient. And then also we can calculate what is happening with the divergence of a vector of A. Remember now the vector of A has indeed 3 components of A rho, A phi, and AZ. And if you do the calculation of these, what you will get indeed, you will get 1 divided by h1, h2, and h3, which is 1 divided by rho. Then you have the derivative with respect to rho of A1, which is A rho. And then you have H1 and H2, H2 and H3, which will be rho. And then I have the derivative with respect to phi of A phi. And then I have H1 and H3, which is equal to 1. And finally, I have derivative with respect to Z of AZ. And then I have H2 and H1, which indeed that will be equal to rho. Okay. And finally, that will be 1 divided by rho, derivative with respect to rho of rho A rho, plus 1 divided by rho, derivative with respect to phi of A phi. And last term, rho will be out of the derivative, so it will be derivative with respect to Z of AZ. And in the same way, you can do it with spherical coordinates, and you can do it also for the curl, and also we can do it for spherical coordinates. So I think we are okay with the time. I don't want to take too much of your time. I will stop the recording and also the live, and then I will answer to the questions that you may have.